My name is Maria, and today we will look at the intersection of network science and cybersecurity. In this talk, I wanted to ask how can we visualize how training data gets poisoned with networks? So machine learning models, they've become increasingly integral to our software applications. They also face increased risks from adversarial attacks, notably data poisoning. So after experimenting with data poisoning, I noticed that training data fed into machine learning models resembled graphical information that could be defined with a visually represented network. My presentation will go further into that concept of data representation and how attacks can modify or poison networks. So here's a quick overview of what I want to talk about today. I wanted to give you some background on data poisoning and network science before we can go further into how we can use network science for threat detection, specifically for data poisoning. Then we'll look at two case studies that will go further into the application of how we can poison networks. After that, I'll go into some future work and refinement. So as defined by OWASP, data poisoning is an attack that occurs when an attacker manipulates the training data to cause the machine learning model to behave in an undesirable way. Data poisoning occurs by altering data within three methods: addition, modification, or the deletion of data. Interestingly, addition can also mean the injection of data, but injection attacks, as we know, do not always mean adding data. Use of injection attacks can often delete or modify data as well. And to demonstrate the addition of data, I wanted to share a story of how a privacy-focused colleague once explained to me how he associated his name to the alpaca by changing his picture across social networks to those of alpacas. So my colleague started to post images tagged with his name or username to alpacas rather than his own face or likeness. So for example, he would tag himself in a LinkedIn post with a picture of an alpaca instead of a human, any human. But by associating his name or username to alpacas rather than his face, my colleague kind of caused an unexpected outcome of the data, essentially manipulating his likeness. So this story, along with some experimentation, led me to ask the question, how can I visualize the change between untouched data and manipulated data? And this question led me to ask another question of how we can visualize data poisoning, and how do we do that using network science? So before applying network science to data poisoning, we should first define some key terms of network science and its significance as a tool. Various systems can be defined by networks, such as the World Wide Web, the nervous system, and even flavor components of food. So this is a cool network. All these ingredients map to various flavor compounds, and you can kind of see how it's statistically represented in this network. You can see that garlic is used in a lot of different foods, and its compatibility with other foods is represented. That one on the top right is starch, which I feel like would be compatible with a lot of foods. So I don't know why it's up there, but so these examples can show how behind every complex system is a network that defines the interactions between its components. And mathematically, graphs are representations of such networks. Networks are defined by, okay, there we go. So networks are powerful tools for prediction, but they're only as accurate and as stable as their data source. So paths or, I think I skipped a slide. Okay, yeah. I just wanted to mention that nodes are the representations of the objects of these vertices, and these edges are what connects them. They are also known as links in networks. So networks are, as I said, powerful tools for prediction, but they're only as accurate and as stable as their data source. Paths are sequences of nodes that are connected to each other with edges. So think multiple edges in a sequence. Analysis of networks leads to these interesting statistics, such as edge multiplicity. That's multiple edges that kind of all connect to the same node, so they all share the same node. Edge multiplicity represents the intensity of certain connections within the network, which can be visually represented with thicker lines stretching between the nodes. Conversely, sparser lines means less edges between the nodes. So for example, we could represent the flight paths on a map as a network. And if you think about the nodes being airports, more popular nodes, such as New York, London, would have thicker lines between each other than smaller airports, I don't know, such as Alabama. So there would be less lines going to there, and so the edges would be thinner. I chose networks as a visualization technique because not only do they have predictive power, but because graphs are simply easier to intuitively digest and look at. So here's a demonstration of the predictive power of networks. Paths in networks can reveal information about the network itself. So the US military operations gathered intelligence on Saddam Hussein's clandestine terrorist network using paths in networks. As Saddam Hussein relied on extended family and social institutions for protection, the US military was able to compromise the network by mapping out his closest associates and progressing that way into the center of the network. So in this case, the networks would be individuals in the network itself, and the edges represent the connections. And the thickness of the lines represents edge multiplicity. Another example of edge multiplicity is this picture of Chinese companies with foreign listings. In this picture, Chinese companies are planted on the map as nodes. The edges represent the foreign listings and connections back to China, and the thickness of the edges represents the amount of connections between these various cities. This is another example of the power that networks have in prediction, and this is very similar to that airport example in terms of the analysis of the environment in these networks. So we can use this graph to infer the impact of the various cities on each other, such as New York to Beijing having the thickest lines, implying that there's more connections shared between these large hubs. To recap, networks help us understand complex systems such as the brain, neural networks, and global financial networks. It's also important to reiterate that the power to create predictions using the networks is only as good as the accuracy and stability of the underlying data. If the data is inaccurate, the inaccurate data leads to false predictions and other cascading results, and could lead to further consequences down the line with regards to the bad data. So all this vital information should be protected, as tampered networks and data can have cascading results. Training data can be obtained from various attack vectors. For example, private datasets can be infiltrated through insider threats or sophisticated attacks. And public datasets or repositories are prone to data injection attacks. With public datasets, poison data can proliferate into other models and applications that rely on these public datasets. So in order to make poison data easier to detect, I decided to visually compare healthy networks and poison networks using this tool called GWAPT. But before I get into that whole platform, I wanted to ask, does anyone remember who this is? So for those that don't know, this is Tay, who is a Microsoft chatbot that was released in Twitter in 2016. Tay was designed to pick up our language and syntax via interactions with real people on Twitter. Long story short, within a few hours of launching, it started repeating vulgar and hateful language. The important thing to note here is the intention of the chatbot, which was originally just to be a conversational agent. But over the course of this massive data poisoning attack, it became adversarial. So it started repeating hateful language, which was the opposite of its original intent. So as malicious language was injected into the model, this is an example of a large-scale data poisoning vulnerability. This is like the original data poisoning vulnerability in some cases. But this is like another example of what led me to think, how can we simulate this transformation of good and bad data via networks to show how all of that data relates to itself and to its malicious parts. So I looked into some tools that could help me map out malicious networks. So back to GWAPT. GWAPT is a network visualization and analysis tool used as a desktop application. To use it, one can just upload a spreadsheet with nodes and corresponding sheet with edges. It's also possible to build out your own network from scratch and customizing its appearance. It's also open source, so a lot of people add various algorithms and tools into it to show data in different ways. Since you can also run multiple tabs in a single workspace, GWAPT provides an easy way to compare healthy and tampered data in the same workspace. So with this tool, I just wanted to go into 2 quick case studies to show the difference between healthy and tampered data. So first, to explore data poisoning within networks, I borrowed the Les Miserables network created by Donald Knuth. The novel was written by Victor Hugo, by the way, not Donald Knuth, who is a famous computer scientist. And this network nodes are characters in the story, and the links represent the co-occurrence between these characters. There are 77 nodes, and in the default network, there are 254 links. To poison this network, I wrote a network poisoning script that adds or deletes edges between nodes, in this case, characters. So this would either create additional interactions in the story that wouldn't exist, or they would delete several significant interactions that would theoretically change the outcome of the story. So here's the initial graph. You can see that all of these characters are connected to each other in some way because they've all had some kind of interaction, even one is possible, like Jondrette or something like that. So I'll let you look at that for a second. The thickness of the lines represents the character's interactions, and the size of the node represents how many interactions each character has had. With my script, I poisoned a lot more interactions into the novel, some that shouldn't even exist. So I basically made a fan fiction of Victor Hugo's book. You can see that there's interactions that shouldn't happen. So here I deleted a bunch of important interactions in the data. Some characters are left without any interaction or dialogue at all. And I just wanted to use this case study as something that can tangibly happen when you poison a network. Going into my next case study, I wanted to explore node irregularities in a more technical network, so Java dependencies. This network contains 1,538 nodes, all of which are just Java dependencies. By adding nodes, we can add packages that don't exist. Adding nodes is really simple in this case. However, adding connections between the additional nodes and the existing nodes is better, as from an attacker's point of view, connecting nodes with more edges makes detection more difficult. My network poisoning script would add a single node to a node with multiple connections before adding nodes that were all attached to the originally injected node in order to create a dependency cluster. The script also modified existing nodes with a simple labeling poison by simply modifying the label of the nodes within GWAPT to null. So as a result, the attacker could use this modification technique as an opportunity to include dependencies with malicious packages, for example. Initially, I did a really, really small modification. Remember, this has 1,538 nodes. So how could you even see this difference? So yeah, that's like 3 nodes. You're not really supposed to see that. This is a closer look. So I used GWAPT to highlight these nodes with a contrasting color in order to show the attacker's presence. However, these poison nodes were added in rather than modifying. So what if we modified the edges between the nodes by adding connections that were not supposed to be there? Here, I modified this entire already existing cluster of nodes to be green to demonstrate modification. The attacker poisoned these nodes by altering their data. For Java dependency groups, it could be assigning their values to just null or just having false lines of code. In this case, I labeled these modified nodes with null to demonstrate the poison more clearly. So through my case studies, I just wanted to demonstrate the differences between healthy data and poison data. By visualizing mathematical differences via graphs, we can prove that data has been altered in some way. In addition, we can detect data poisoning by labeling the data that we use. As part of future work, given data provenance materials, I would like to implement visualizing the change between healthy and poison networks, similar to a diff function. So behind every complex system is a network, and behind every network are nodes and edges that define this network mathematically. In order to have these accurate and powerful networks that we use in our day-to-day life, we must protect that data from data poisoning. And by visualizing data poisoning, we can more easily detect tampered data and highlight an attacker's presence within a graphical network. Thank you.
Hi. Sorry, it's not necessarily related to that. I was just curious about when you had the food diagram up there.
Yeah.
Where that came from.
Yeah, that was. Yeah, that came from a research study. I should cite my sources more often.
It's awesome. Thank you.
I had someone, you mentioned accuracy as a requirement and stability. What do you mean by stability?
So I feel like if it's poison, it's unstable. That's what I mean. Yeah, if it's modified in any way, then
You have to have consistent data.
consistent data, yes. And it should be intentionally, if it's changed, it should be intentionally changed rather than unintentional changes. That's what I want to show. So if you intended to make these changes, then that's great. But if the data's been poisoned, then that should be made aware, or one should be made aware of any poisoned data.